Very good. So yesterday we saw that this theory that describes the low energy limit of a stack of D3 branes, which is n equals 4 super Young-Mills, is conformal. So let me recall a few things. That local gauge invariant operators in n equals 4 super Young-Mills include such objects, which are traces of a bunch of letters that form a word. The word I indicate with this A. A would be the sequence, a choice of which fields to use. So A here would be a word, where these letters, chi1, chi2, etc., are all at the same position in space-time. Now, just because this is a trace, is a product of fields, so in the double line notation, we would indicate it like this. It's a product of fields. This keeps track of the indices, how the indices are multiplied. Of course, now it's not just a single matrix, so I need to keep track of who is at each position. So I need to write some chi1, chi2, chi3, or some notation to indicate what I'm doing here. Or I could also draw it like this, but I keep in mind that even though I drew it like a big picture, this is all at the same position x. Right? So don't be confused. This is all just a point. I just blew up to see the index where it is. And this, of course, looks like a closed string, right? This just looks like a loop where I have a bunch of string bits, if you want, all this product of fields. And the picture would be that if we start doing correlation functions of these operators, this would look like, from a topology point of view, as correlation function of closed strings. Right? If you do a 4-point function or a 3-point function, you will draw these planar surfaces that look like the interaction of 3 closed strings. At least as far as pictures goes, that's true. Now, these operators, a cute way of writing any field of n equals 4 was using these creation operators. You had these oscillators, A and B and C, and that's enough. With these oscillators, A carries index alpha of SU2, C carries index A of SU4, and B, we also have B, that carries index alpha dot of SU2. And together, A, B, and C, you can construct any operator that has a given number of R charge indices, A, B, C, and a given number of SU2 indices, alpha, beta, gamma, and a given number of SU2 bar indices, alpha dot, beta dot, etc. And here are all the operators you could construct. You could construct any number of covariant derivatives that are a bunch of A dagger times B dagger to the power k. And then you could construct, they could act on F, on psi, on phi, on psi bar, or on F bar. And then you would have this possibility for the various oscillators. One operator that was particularly nice was this one that we constructed. You see that this is an object that is in the same representation as trace of z square. Why? Because both are symmetric traceless. So from the point of view, they are just rotation, SU4 rotations of each other. Right? I can go from this to this by an SU4 transformation. How do we see it's traceless? You see that this object, it's symmetric because there are just two fields, so it's by definition symmetric. And if I take the trace, which in SU4 language means I contract with this epsilon tensor, here I get the contraction, and here epsilon with epsilon, there are 24 options, so 1 over 4 factorial kills those 24 options, and I get contraction minus contraction, so it's traceless. So it's traceless, it's symmetric, so it's in the same representation of this guy that is also traceless and symmetric. And being traceless and symmetric, and having maximal R charge, implied that this operator were killed by some supersymmetries. They were therefore in shorter representations. They can't move, and they need to stay in shorter representations. So delta needs to stay equal to j plus 0. Because delta equal to j was the condition that you are in a short representation. And so this operator, as I mentioned too, you act with a bunch of q's. I wrote schematically there q to the 4. You get f squared, that therefore is dimension 4, because each q raises by 1/2. And but this guy, by supersymmetry, is related to the Lagrangian. In other words, all terms in the Lagrangian, you can go from one to the other by supersymmetry. And so the Lagrangian needs to have dimension 4. And therefore, this coupling that multiplies the Lagrangian density as dimension 0, and the beta function is just 0. And so n equals 4 is a fully conformal theory. Okay, now what we are going to do today is try to think of these closed strings, these operators OA, and start studying correlation functions. Start see what is the physics, what happens in the n equals 4 supreme Mills if I take two such words, OA at position x and OB at position y. That's what we want to do. Okay. Now, this operator has classical dimension equal to, okay, this has some classical dimension, let me call it delta A, that's going to be the same as the classical dimension delta B. Now, to be concrete, let's choose the following operators. Let's say that chi A are equal to operators that are made out of the scalars only. So this A stands for a sequence trace pi m1 pi mj. So A stands for that sequence m1 up to mj. Then these operators here have classical dimension equal to j. Do you agree? So they will have classical dimension equal to j. And now what we are going to do is we are going to compute their correlation function. So this operator is, if I draw it in our double line notation, something like this, where here I have phi 1, here I have phi 2, and here I have phi j. And this would be my operator OA. And OB that I contract with is a similar operator. Sorry, I wrote 1, I meant phi m1. Phi 2, it's phi m2. It will be one of the 6 scalars. And phi j, phi mj. And upstairs, I have OB that would have 1, 2, 3, 4, 5, 6. Also 6 fields. Otherwise, I cannot contract. 3, 4, 1, 2, 3, 4, 5, 6. And to leading order, all we do in perturbation theory is contract these fields. Now, because I contract these fields, I have here a phi n1, a phi nj, and because we just contract them, we get that this diagram here would be, there will be a Kronecker delta that says that m1 needs to be equal to n1, m2 needs to be equal to n2, delta, mj needs to be equal to nj, and then there would be a propagator. There is some overall normalization. It's not very important, but okay, we can write it. G squared to the power of number of propagators, j. There are some loops of n that we draw here. One loop here, one loop here, one loop here. So j loops of n to the power j, right? There's one loop outside as well. So there are n loops. I draw like this. And then each propagator is 1 over x minus y to the power square. So there are j propagators to the power 2j. And so this thing here, I can write as saying that the word A needs to be equal to the word B. Maybe I can put them both downstairs. A and B need to be equal. And that would be what we would get.
Question.
Yes?
This might be a silly question, but like, why don't we deal with permutations between N1 and M2? And...
Okay. So now, here, notice that by planarity, the lines need to contract directly up. So what we could do, what we cannot do, is contract this leg with this leg here. We cannot just swap and connect this one with this one here, because to do it, we'd have to go to pass by the other legs. And so by planarity, the lines need to connect directly up to up. Right? Now they could all rotate here, right? They could all rotate, but since we are dealing with a trace, the state here should be cyclic, and so there should be no difference in rotation. And so we don't need to assume this rotation. Okay. Right? Now, and so planarity, note that this structure here is crucial. So here, what we are doing is studying the large n limit, and we are very strongly assuming planarity. We are using planarity to say that this is what we get at large n. Right? So again, this diagram where the legs would do something like this, and then the other ones would contract like this. This would also exist, but it would be much suppressed in n if I do something like this. Right? So this diagram is much smaller than the planar one. It has less powers of n. And so planarity, what it's giving you, if you think of this as the cylinder of the string, planarity gives you locality on the string. Are there two L's or two T's? Local, is it okay? Locality? Yeah? Okay. So planarity gives you locality, right? Things cannot on the string interact far away, right? There is some notion of things that are nearby, they can interact, but not things far away, right? So it gives you locality on the string surface, which is the string worldsheet.
Here we are contracting things like in Fick's theorem we are contracting fields. So why not the same operator with OA contract with them phi with phi in A itself? Why it has to go to
so operators in quantum field theory, when we draw OA, we never allow for contractions between the same field. That we never do. So that when we renormalize the operator, typically we use some notation like this when we write the operator. So in other words, in this OA, if you want to keep in track that you should not do self-contractions, those would be divergent, right? A propagator between the operator and itself is 1/0. Sometimes we put some dots like this to indicate these are really composite operators. So a composite operator is different from starting with two operators. There you would contract and then joining. In a composite operator, you remove self-contraction. You don't do that. And so this object is equal to this at what we call tree level without loops. Now, what happens at one loop? So we conclude that the propagator OA OB equal, there is some overall power of the coupling, lambda to the j. There is some propagators, x minus y to the 2j times delta EB. That's what we got so far. Now at loop level, several things start happening. So now at one loop, let's draw what could happen at one loop. So again, we have our operator. And here we have the operator in the bottom. And at one loop, it means we are going to start using the vertices of n equals 4. Right? So we are going to use the vertex once or twice, right? We are not going to, it's one loop. Right? So we are going to bring down a quartic vertex, or maybe bring down 2 cubic vertices, but that's it. And because of planarity, things are going to happen somewhere here in the middle, say, but then here, far away, we still just contract. So there is a part that by planarity, again, nothing special must happen. Then let's say things will happen here, and so here nothing will happen. So by planarity, things are always localized in some small region. Now let's draw what could happen in this region. Well, we have a phi to the 4 coupling there, right? Phi, 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 phi. Right? And so they could couple here. We could have a 4-point vertex here. This comes from the commutator that's there. That's the only term the only interaction term I wrote. Actually, not the only one, but let's draw. So this is one possibility. Now there is another one that there is another interaction written here. This is one of them. This is done. There is another one. So where is it? Here. So what is it? What kind of interaction is it? If I draw it graphically.
A2 phi 2.
Sorry?
A2 phi 2. Something should come from outside.
So there are two types of there are two possibilities here, right? That involve the gauge field. What's the simplest one? How many phis do you have? And how many a's? How many gauge fields and how many phis? Here. There are two possibilities, right? When you write a covariant derivative square. Either you have 2 phis and 2 a's, or 2 phis and 1a, right? There is a cubic coupling and a quartic coupling, right? So, for example, a diagram we could have is also for example, I don't know, let's a cubic, a gluon. I'm drawing the gluon wiggly, but double line, like this. That's one possibility. Another possibility. Right? Another one is, instead of this wiggly line connecting one line to the other, I could have the wiggly line could just connect with the same line. I could throw a glue and then catch it later. Right? Really? And so, and there are more. Maybe I can just focus on this line. If I just focus on this line, I could have, for example, there is this Yukawa coupling that two fermions can couple to the boson. And so we could have, for example, in that line, something like this, where this dashed line now is are fermions. And the dot, dot, dot here, dot, dot, dot here. I'm just representing this line here. The rest is the same. Plus, there could be perhaps a few more options. Now, it's a lot of diagrams, right?
Where is the case that we have 2a, 2 phi?
Sorry?
Where is the case that we have a to the power 2 and phi to the power 2?
I did not draw, so it's here in the dot, dot, dot. Let's draw it. So it would be something like this. And then there would be two gluons getting out here. And they do a bubble. Then the other lines do nothing, right? You agree? Now, notice now something very important, which is that gluons don't carry SU4 charge. So whatever these diagrams give, if this index here, if here I have phi m, here after the gluon interacts, I must also have phi m. The gluon cannot change the SU4 charge. The gluon is neutral, right? Doesn't carry any, when in the coupling there's no, right? There is phi m, and the d mu doesn't carry any R charge. So R charge is conserved. And so the gluon, let's put a square to indicate it's the same. This gluon is the same as this gluon, and this gluon is the same as this gluon. Similarly, this gluon is the same as this gluon. And of course, the other ones as well. This gluon is the same as this gluon. And here as well, this gluon and this gluon are the same because it's just one leg. Something happens, one index of R charge goes here, the other goes here, fine, but then they recombine and R charge is conserved, so this index is the same as this index.
Sorry, gluon or scalar?
Yeah, I meant the scalar. The solid lines are scalar. So this scalar is the same as this scalar is the same as this scalar. If I said gluon, I meant scalar. It was a gluon in 10 dimensions, but now it's a scalar. So you agree that it carries some R charge that is conserved, and therefore it's the same here and here, here and here, here and here, here and here. Also here and here, because it's just one, this line, this index m must go to some index n, but the only thing that can happen is delta mn. Now here it's a little bit subtle because you have, if you think of this as phi a, as two indices a, b, they split. One goes to one Fermi and one goes to the other Fermi. But okay, fine. Then they recombine and they give the same index, right? The indices are conserved. So similar here. If I have this scalar here, it's going to be the same as the scalar here. So all these diagrams that we draw, except the first one, all these ones, everyone here, plus dot, 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 all these ones, they are proportional to the same delta AB that we had at tree level. Right? Whatever is in the bottom, the word in the top must be the same. Okay? So they are equal to delta AB times something. Let's call it I for incognito. But from the point of view of indices, it's proportional to delta AB. Now we are going to find I by an indirect argument. And the idea is we just need to focus on this diagram. If we do this diagram, then we can get I through a trick. Because we know it's proportional to delta AB. And so this diagram here is all we need. But we did this computation already, right? You remember, we did it. It is just two propagators of phi that go here, two propagators of phi that go there. That was the phi square of x, phi square of y correction that we did already. Right? When we were doing things. Now we only have to decorate by the indices. So we just need to keep track of the indices. So let's do that part. Okay, I can do it here. So the result is the following, plus, and now this diagram here gives you what? It gives you the following. Well, let me write the result. You can tell me what it was, but it was something like this. Well, it was. Okay. Let's first compare this diagram with a tree-level diagram and see that this diagram has two extra propagators compared to just connecting the line straight, and one extra vertex. So in total, it has an extra power of g squared. Do you agree? Because each propagator is g squared and each vertex is 1 over g squared. So 2 more propagators, 1 more vertex, so 1 more power of g squared. And how many more loops you have in n compared to just connecting the line straight? 1 more loop, right? You had 1, 2, 3. Now you have an extra one here. So 1 more loop. So 1 g squared and 1 n. So it's a 't Hooft coupling. Right? 't Hooft coupling is g squared times n. So perfect as we wanted. Things organized nicely with 't Hooft coupling. And then what we have this loop diagram. And this loop diagram was giving this logarithm of the distance between x minus y squared divided by epsilon squared. And then finally, we have to be careful with the indices. If this index is m and this index is n, m prime, and if this index is n and if this index is n prime, there will be here some tensor that we are going to compute in the next blackboard that will be a given number for different m prime going to n prime. And everyone else, you just connect with delta function. So then we have a delta, let me write like this, a prime, b prime, where this prime stands for the other indices. Okay. And then plus the other diagrams that we said are I, this thing that we don't know. It will also be proportional to the 't Hooft coupling. Let me put a lambda here explicitly. Times delta AB. And here, if we do the computation carefully, there should be some total pi's remaining that I don't know by heart, but probably some 1 over pi square, maybe 2 over pi square. This was just from doing that Feynman integral, right? There is some pi's there. Okay, so what is this tensor here? So let's work it out. Now, the scalars, now there are a bunch of options that these scalars can connect. And when they connect, one thing that can happen is that m, so we have this, let's write this vertex, pi m, pi n, which is pi m, pi n minus pi n, pi m square. And so this vertex is equal to the square of this term, pi m, pi n, pi m, pi n, plus the square of this term, but we are computing this inside the trace. So inside the trace, the square of this term and the square of this term is the same, right? Because it's alternating. So just 2. And then we have the cross term, which gives me minus 2 pi m, pi n, pi n, pi m. In other words, I can put the phi m here in the middle because it's in the trace. You agree? And so from the point of view of just following the vector index, you would draw this, you would say it's a diagram like this, where if I follow the trace, if I write this inside a double line notation, I draw the double line, but then inside I say where the index goes. This scalar goes there, and this scalar goes here. This would allow me to keep track of the indices, right? But then I'm erasing the double line and keeping the interesting part now, which is just the SO6 index. So from SO6 we get this. While here we contract the 2 neighboring guys, and so here we get this vertex, where from the point of view of SO6, it would be the 2 neighboring lines that reconnect. Correct? Do you agree? And so now here, when we have this index, this here, m prime, n prime, there are a bunch of possibilities we could write. One option is saying that index m becomes equal to index n, and index m prime becomes equal to n prime. That's one option. The other option is that delta m becomes equal to, say, m prime, and delta n becomes equal to n prime. And the last option is that delta m becomes equal to n prime, and delta m prime becomes equal to n. And now we should work out the relative coefficients between these possibilities. So this one, where they connect like this and like this, which vertex should I use? The first or the second? To get this possibility.
Second.
The second, right? I need to connect this vertex where they connect like this and like this, right? And I can connect the vertex with this being in the bottom or these two being in the bottom. So there are two possibilities. And there is a -2 here. So in total, there is a -4 here. What about this one? M goes with m prime and then goes to n prime. Should I use the first or the second?
Second.
Second as well. And again, I can connect the vertex like this or flip it around, which is the same thing, and connect it like that. So again, -4. And what about this one? Now, the first, right? Because they connect cross, right? And any rotation of the vertex gives me the same thing. So there are 4 possibilities. So +8 times that. And so this thing here is that tensor T m prime n prime. Right? This is that combination up there. And so in sum, we conclude that if I have some O A O B, it's going to be equal to some number lambda to the j over x minus y to the 2j. And then there is just delta AB, which is delta, let me now write explicitly, m1 n1 dot delta mj nj, the first term. And then there is some minus, okay, or maybe plus, doesn't matter, plus or minus 2 lambda over pi square times some logarithm of x minus y squared divided by epsilon squared. And then this logarithm multiplies a structure where I sum over small j, and then for the most part, I get Kronecker deltas. M1 goes to N1, delta M up to position j minus 1 goes to N j minus 1. Then here, I insert this tensor T mj plus 1, nj plus 1. Sorry, I don't want to close the parentheses yet. Then, let me put here. And then I have delta of the n m j plus 2 go to n j plus 2 delta m capital J goes to n capital J. So this almost everything contracts directly except here. And there was also the contribution from I that we did not know exactly, but it's some term here, some constant, times delta delta, where they just contract directly. Mj goes to Nj, and Mj plus 1 goes to Nj plus 1. Right? Yeah.
How do you know that? And we know that because the one loop calculation is universal, it's going to have the same spatial dependence.
Right. So we know that by dimensions, all these one loop computations, we know we are dealing with a CFT, so we know we are going to generate the same logarithmic dependence. And indeed, you can see that maybe it's not totally obvious, but all of them will generate the same log dependence. So you would have to do some counting to see, is this diagram also giving the same type of logs? Yes, and so on. All of them will give the same type of logs. But what matters is, for this purpose, that they have this index structure like that. So in summary, what we see let me write in a notation that's perhaps more intuitive, that OA, OB is equal to some three-level expression, something doesn't matter, divided by x minus y to the 2j. And then there was this delta AB minus lambda, the log of x minus y squared divided by epsilon squared. But now, instead of a number, like we were getting in our toy example of phi squared, etc., we are getting some big matrix H, AB. Plus, and then, okay, at one loop, it's this. Right? Remember, in the example we did versus the example we did before, which was a toy example, phi square with phi square. It was giving the similar thing, but here it was 1 instead of a delta. And here it was the same thing times a number instead of a matrix, right? And okay, here we add minus lambda log of the same thing times a number. And you remember the conclusion here in this line was that this phi, we could define some O of x that was phi square of x times epsilon to the power lambda times this hashtag, and then this operator at dimension, which was 2 plus lambda hashtag. And this was the quantum correction to the dimension. Right, so this is what we had before, and this is what we have now, right? So how do we go from what we have now, which is more complicated, to what we had before? What should we do? Instead of 1 and the number, we have delta AB and the matrix.
Diagonalizing the matrix?
We diagonalize the matrix, right? So if you diagonalize the matrix, we go from the first line to the second line. So it's clear what we should do. We should first find the operators O that are defined as some linear combinations. Let's use psi A OA, some linear combinations of these operators OA, where these psi A are chosen such that they diagonalize this matrix HAB. Right? So we take linear combinations such that when I plug these linear combinations, I diagonalize this HAB. Right? Then, with this operator, this equation here becomes that the expectation of O. Now, maybe let's write like this. These operators O, there are a bunch of them, right? You diagonalize a matrix, you have many. So let's put here On. So that On with OM will be equal. Well, N needs to be equal to M, delta Mn divided by X minus Y to the 2j. And then we get 1 minus lambda times the eigenvalue, the n eigenvalue, times log of X minus Y squared divided by epsilon squared. Because we diagonalized. Right? And now we just define our O renormalized and to be just epsilon to the lambda gamma n times On. Right? And then this operator On renormalized with OM renormalized. Now it's what we expect in a CFT, delta Mn divided by X minus Y to the dimension n, where delta n is just the same delta classical, that was J for everyone, plus the anomalous dimension n. And so what we need to do is diagonalize this matrix, and then the eigenvectors of the matrix tell you what are the good linear combinations, what are the good primaries that have definite dimensions. So the eigenvectors give you the operators, and the eigenvalues give you the dimensions. Right? Now, notice that now there is a convenient way of thinking about this operator. We can think of this H, we can think of it as a quantum spin chain Hamiltonian. So let's explain this. How do we do this? We just think of our operator, OA. I think of it as a spin chain where in the first side I have a degree of freedom M1, in the second M2, in the last one Mj. So it's an SO6 spin chain where this value takes value 1 to 6 and so on. So this is an operator. This is a cat that lives in the product of V tensor V, where each of these V's is just some 6-dimensional object. This will be the Hilbert space. You agree that OA is equivalent to this, just notation. This is the same as trace phi M1 phi Mj, right? They have an order, so I can just write it like this. Just saying that I have position 1, position 2, position 3, etc. And I just keep track like a cat, like this. And then my H acts on this vector with index A and gives me a vector with index B. So it acts on this spin chain. And then how does this H act? Then my Hamiltonian of my spin chain, H, the object that I need to diagonalize, you see that it does nothing except locally at positions n and n plus 1. So this H is a local Hamiltonian. It's a sum from n equal to n up to the size of the spin chain. And then it just acts with an Hamiltonian density at positions n and n plus 1. Otherwise, it does nothing. This locality came from planarity. And then what does this Hamiltonian do, this Hamiltonian density? It acts on two neighboring spins, m and n. Right? Maybe we can put a lambda outside here explicitly, a Tooth coupling, so that we don't worry about it. Maybe some lambda over some pi square. We don't care about the pi square. And then what does this Hamiltonian do to the spins? Well, it can permute the spins. It can swap these two spins. So it can give n and m. That swapping of the indices comes with coefficient 8. So let me normalize and say coefficient 2. I normalize by, I put the 4 here. There was a 2 pi square. There's a 2. So this would be what we would say. It's 2 times the action of an operator that permutes the two sides. This is what's called the permutation operator. Then it can annihilate this and produce any number of them, or it can, this one here, or it can do nothing. M goes to n and m prime goes to n prime. So there is another term which is plus. This one is something that I'm not sure, times m and n. This would be something times the identity operator acting on mn. This I don't know because it comes also from this incognita term that we did not compute. Right? The identity part is the part that receives contributions from the incognita. This I don't know for sure. This I don't know. And then the last term is plus. It could produce any E and P if m is equal to n. Right? This would be this possibility of n equal to n prime. It's this term here. That compared to this one that gives 2 would come with a coefficient minus 1. And this would be the definition of the so-called trace operator acting on m and n. So these two operators are the usual operators you would write in an SU2 spin chain, that all you could do is swap the spins, is hop the spins and do nothing. And this is something new that you would do in spin chains that have SON symmetry. You can annihilate the spins and create any pair of spins. And so we conclude that this is our spin chain where this Hamiltonian density is then twice the permutation operator on sides n and n plus 1 minus the trace operator on sides n and n plus 1 plus some number times the identity operator acting on sides n and n plus 1. And so we conclude that we have a local Hamiltonian and nearest neighbor Hamiltonian. And if you diagonalize this local Hamiltonian, you get the eigenvectors and the eigenvalues. And in particular, you get a spectrum at one loop of n equals 4 super Young Mills in this scalar subsector. Is it clear? Now, of course, so now we want to ask, what's this constant? So we finish our game. Right? And that's it. And then we want to say, what can we do with this problem? How can we make progress in this complicated problem? Now, how could we go about computing this constant? Any suggestion? What is this constant? This constant is equal to -1 plus whatever the other diagrams give, right? But that's not very convenient because we don't know what the other diagrams give. So how could we try to fix this constant by another argument? So first notice that this constant is just an overall shift of all the energies because it's proportional to the identity, right? So we solved the most interesting part of the dynamics is done. Right now we just have some Hamiltonian that there is some overall ground state energy that we don't know exactly where it is. So how could we go about fixing this overall shift?
We fix it to 0 to make ground state become 0.
To make what?
The energy of ground state becomes 0.
But why would we do that?
We like this.
Why?
Most of the time it's good to have 0 energy ground state.
Sometimes it is, yeah. Sometimes you should.
Could you use the fact that like f squared receives no quantum corrections to try and cancel?
F squared doesn't is not an operator made out of scalars, right?
Oh, right, yeah. Or the
Z to the J.
yeah.
Good idea, right? So now we can use the fact that Z to the J should get no quantum corrections. Right? But trace of Z to the J should or must have gamma equal to 0. So let's see how it works. So this operator here, right? It is just Z, Z, Z. Trace, right? And you can ask now, what happens when we act with the Hamiltonian density on this pair of Z and Z? Right? Locally. Well, if I go to that language where we know how to act, this object, like we said before, it's 1, 1, minus 2, 2, plus I 1, 2, plus I 2, 1. Right? So now let's just act on this operator. So first of all, the trace. What does the trace do acting on this operator? What does it give? 0. We said they are symmetric traceless, right? That's why we argued this was the same representation as this. Indeed, it gives 0. We see explicitly because here 1 is not equal to 2. And when it acts here, it gives the same as when it acts here. So it just cancels. What does the permutation give when you act here compared to what the identity gives when you act here? The same, right? Both the identity and the permutation give back the same state because this state is symmetric. Right? And so the Hamiltonian acting on this state just gives me 2 minus that number that we don't know times ZZ. So this number is equal to 2. And so we conclude that the dimensions of these operators, trace, phi I1, phi ij, are equal to the energies of a J-site spin chain with a local Hamiltonian H, which is just some overall normalization, some lambda, this I'm not sure. And then that would have to do the diagram carefully, sum from n equal 1 up to j, and then the local Hamiltonian density twice the permutation operator acting on sides n plus 1 minus the trace acting on sides n and n plus 1 minus twice the identity operator acting on sides n and n plus 1. Now, this is still not trivial. It doesn't mean we solved completely the problem. Solving this spin chain is still hard because we have, of course, a 6 to the j times 6 to the j matrix typically, right? It's still an exponentially hard problem. If you have 6 scalars, you have a huge Hilbert space, right? You have 6 options at each side. It's a complicated problem to solve still. Now, some problems in 1 dimensions of quantum spin chains are better than others. Some problems are exactly solvable. And some spin chains are integrable. Some spin chains can be exactly solvable. And so now you can go to a book and ask which spin chains with SON symmetry are integrable or with SO6 integrable are integrable. And what you find is that if this coefficient is minus twice this one, so if the ratio, this ratio, which is equal to minus 2, is precisely what says that this spin chain is solvable. And this is the beginning of a big story that we are not going to go over. This was a discovery by Minahan and Zarembo in 2003 that they did this computation and they found exactly this number 2 and minus 1. And they said this is exactly the combination that allows us, of all possible ratios, this is the one that allows us to solve this model. And therefore, they could compute exactly in a very simple form all these eigenvalues of the spin chain.
Sorry, is that an if and only if? Being minus 2?
Yeah, it's integrable only if the ratio is minus, maybe if the ratio is 0, it's also integrable, if there's no permutation. That's another type of Leib spin chain. But if they are both non-zero, the ratio needs to be minus 2 for the model to be integrable. And why is the ratio minus 2? Because it's not any random theory, it's this theory with this precise commutator square. And why was this precise commutator square? Because it came from 10 dimensions. And it was just a trivial f squared in 10 dimensions. And why was it in 10 dimensions? Because it came from string theory. Right? So it's a gift from string theory. Really, the disintegrability is really a sign of, is really a sign of that this theory was a theory coming from a higher dimensional theory that was string theory. And so what we see here appearing is this big field of integrability. I think you are having some courses on integrability, right? With Kevin? No? Not this year? But integrability is a big subject in physics that some models in 1 dimensions can be exactly solvable, like these quantum spin chains. And what this leads to is to knowing the spectrum analytically, and not only at 1 loop, but this problem of computing the spectrum for any coupling lambda is solved. Okay. Of course, this is a big arrow. It will take a full course just to explain. We just did 1 loop for a subset of operators. But let me just say a few words about the full problem. So first of all, there are 2 things I could, 1 more minute please. Just 2 things we could say. One is how to go to all operators, not just scalars, but we could generalize to all operators. And we could also generalize to all loops instead of just 1 loop. Right? And of course, that's both are interesting and both are non-trivial. And then there is the question of how do we solve this? How to solve it? And that's where integrability would kick in. So just to finish, and because we have the material here in these blackboards, let me just tell you, because there's a beautiful spin chain that describes all operators at 1 in n equals 4 super Young mills. We found this SO6 spin chain, and now I could tell you what is the general spin chain for any type of operator. And so here it is. So the idea is the following. Now we have a spin chain that now our spin chain states psi. Instead of having an integer m1 up to mj, now we have a letter chi1 up to chi_j at each site where chi is one of those operators. Right? So it's already, you see, it's a non-compact spin chain now. Right? In particular, because we can put any number of covariant derivatives. So it's an infinite dimension. So a way of thinking, okay, now, so this is the first thing. Now the Hamiltonian will be, by planarity, a sum of Hamiltonian densities acting on sites n and n plus 1. Okay, so that's just by planarity. Then this Hamiltonian density, let's put double line, acts on the words chi and chi prime and gives some number c times chi prime prime and chi prime prime prime. Right? Do you agree? Now the rule is the following. Suppose here, in these operators, you have some oscillators. Right? You write them with oscillators. Right? And here, you have other oscillators. And then what you do is you move to write these new fields. They have different oscillator content. And so what you do is you move n 1, 2 oscillators from this side to this side. And you move n to 1 oscillators from this guy to this guy. That's a way of getting these operators chi prime prime and chi prime prime prime. Now, which ones do you move? Do you move A daggers, B daggers, C daggers, or what? It doesn't matter. You just tell me that you move n12 from here to here and n21 from here to here. That's all I need to know. Then this coefficient depends on n, n12, and n21, where n is the total number of oscillators. Again, just to be concrete, if these are scalars, there are 4 oscillators in total. N would be 4 in this case, if it acts on 2 scalars. And then when it acts on 2 scalars, I get 2 scalars again, but I can reshuffle the oscillators, and therefore this n12 and n21 could be whatever they want to be. And you sum over this n12 and n21 that reshuffle these operators. Right? And it turns out that the full quantum spin chain can be just summarized, can be just given if I now give you what these C's are. And so this is that you just need to know the total number of oscillators. How many oscillators? So this is the total. This is the number that go from chi to chi prime. You take some from chi and you put it in the other slot. And then you have n21. This is the number that you take from chi prime and you put it in the chi slot. Right? So you take some from here and you put here, some from here and you put there. And this result that encodes any possible state is just equal to the -1, that is, okay, a boring -1, I'm not going to write here in detail, times the beta function of n1, 2 plus n to 1 over 2, and then 2 plus n minus n1, 2 minus n to 1 over 2. If n1, 2 and n to 1 are not equal to 0, and it's equal to the harmonic number of n over 2 if n1 plus and n2 are both 0, where this harmonic number is just the sum 1 over k up to n. And this beta function is just a bunch of gamma functions, right, that you probably saw in string theory. And this is the full spin chain that now describes any operators acting. This is called the harmonic action. And this spin chain, of course, I already told you, is also an integrable spin chain. And so the full one loop problem can be solved. So it looks non-trivial, but if you restrict to just scalars, this fun expression becomes what we just described there for the scalar. If all you have is 4 oscillators, and you can just move these 4 oscillators around, and you work out the weights, you would get this 8 minus 4 minus 4 that we got before from just summing over these possibilities of reshuffling the ends. Okay, so I think this is a good point to stop. Sorry for going over time, and let's continue tomorrow.